right, hello everyone. Thank you for making it out. I hope you've had a great Google I/O so far, and thanks especially for staying till the end. You're very dedicated. I'm Cameron. I'm the product lead for the Go programming language at Google. I'm here with my colleagues, Michael, software engineer on the Go team, and James, product manager for Cloud Serverless. We're here to show you how to boost the performance of your Go applications with profile-guided optimization, or PGO, including on Google Cloud. So real quick, how many of you use Go today? Either yourself or through your teams? Almost all of you, I think. And how many of you have used PGO or have heard of it? Oh, not too many. Great, so you're in for a treat. One thing is it's not about AI, so that'll be fun. We'll show you how it is. Before we dig into it, I'm going to spend a few minutes sort of zooming out to tell you what Go is, what we, the Go team, think Go is, and how we use that to look forward. And the first and probably most important point about all of that is that Go is not just a programming language, it's a complete end-to-end platform for building production systems. This has been our vision from the very start. It's to facilitate real software engineering at scale. That sort of software is written in teams where members come and go, where there are deadlines, SLAs, all of that. And internally, we reduce that vision to the mission statement in the title of this slide. Go provides the most productive platform for building production systems. So we say it's productive because it's easy to learn and maintain, scale across teams. It's a platform because it's more than a language. It's an end-to-end developer experience. This includes IDE integrations, build and deployment tools, monitoring tools, runtime tools, vulnerability scanning, all that right out of the box. And it's production ready because it's reliable, efficient, stable, and secure, which is why you'll see it all over the enterprise, especially in the critical business systems and infrastructure, all throughout the cloud. And it's actually why the modern cloud itself was built on Go. And by that, I don't mean just Google Cloud. I mean all the major cloud service providers and all the other major players in cloud tools and technology. So thinking about that some more, how many of you are familiar with the DevOps infinity loop diagram on this slide? Half of you. So it's like a decent way to think about the sort of broader software development lifecycle. You've got the loop on the left as like the inner dev loop. So this is where you're writing code, you're iterating quickly, you're looking for quick feedback and productivity. And you can think of the loop on the right as the outer loop, the one where you've deployed your code, it's into production, now you want to monitor it and operate it. So when we think of Go as a platform, we think about solving end-to-end across this whole thing, the inner and outer loops. So I'll make the point with some examples. Let's take developer velocity. Go has features and tools and libraries that take everything into account to maximize your team's developer velocity from when they're writing code to pushing it into production and then operating it reliably thereafter. We provide IDE integrations, including our own plugin for Visual Studio Code to make it easy to leverage the features of the rest of the tool chain. We provide a powerful concurrency model through Go routines. We have built-in formatting, a built-in test framework, a built-in debugger. The Go compiler itself builds static, standalone binaries with no system-wide dependencies or a separate runtime, which makes deploying easier, safer, faster than in other languages. It's an end-to-end solution for gaining and maintaining developer velocity. Next, let's take security. So Go is a well-known leader in security, which we also address end-to-end. If you've been following the latest news on the XZ software supply chain attack, you'll know, how important this is, and perhaps it's more important than ever. This is one area that we've taken extremely seriously because we've seen what can happen in other language ecosystems when a popular dependency is compromised. And because Go is used in all of this critical infrastructure in the cloud, we recognize that security is among the very most important things that we provide. So this starts with our dependency management system, where we got the Go module mirror, the checksum database, the package website at pkg.go.dev. They all warn you if a library that you depend on is tampered with or suffers from some known vulnerability. And how this works is actually very interesting. It's beyond the scope of this talk, but I encourage you to check out all the material we have online about it. Our IDE integrations go deep. If you use our plugin for VS Code, you're alerted to vulnerabilities in your dependencies right in the IDE, including whether or not you're actually invoking those vulnerabilities from your code. So this way you know all about the security posture of your dependencies before you actually rely on them in production. Go is also the only major language with fuzz testing built into and integrated with its toolchain. So fuzzing is like an automated type of testing which intelligently manipulates the inputs to your program to find bugs and vulnerabilities. And then we have Go's compatibility promise, where we ensure no breaking changes starting all the way from Go 1.0. So this means that upgrades are easy, which makes staying up to date with security fixes easy and keeping up to date with enhancements easy as well. So we built on this a little bit last year in Go 121 with forward and backward compatibility features. It's all part of this bigger message where we really think of compatibility as more than a convenience. It's a critical security feature. And the last example I'll walk through is for performance. So Go's standard library is rich and robust, and it's optimized for performance. And you can really build anything without having to import some heavy library or framework on top of it. We also have a self-tuning garbage collector. If you've ever spent time tuning a garbage collector in Java, you know that it's like a full-time job. Like it can take as long as it did to write your code in the first place. In Go, the garbage collector is performant out of the box, and it self-tunes to fit your workload's needs. And of course, PGO, Profile Guided Optimization, which we'll spend the rest of this presentation reviewing. Michael, my colleague, has a really interesting discussion next on the Go compiler and how it makes optimization decisions, and then how PGO provides a means for it to boost that even more. So I won't get ahead of them, but I'll just say that customers who've used it love it, and some have seen some really impressive performance improvements. So before we do that, focus on PGO, I'll just add there's a ton more. All of it fits this framework of end-to-end solutions out of the box. And that's what makes Go the most productive platform for building production systems. And we do all of this with really extraordinary feedback from our users. For the most part, Go users really love Go. And we consistently see this. We see really high customer satisfaction in our surveys, levels that are practically unheard of in the industry. So I'll just close this section with a quick overview of how we position these features in Go as value to you. So in these 4 rows, you can think of this top row as stuff relating to productivity. It's quick to get started. It's quick to iterate. It's quick to build real scalable production applications. And that all translates to faster time to value for you. The second row is about reliability, which includes security and compatibility and all the stuff that reduces your long-term maintenance and operation burden. So the less burden, the lower your total cost of ownership, and the more time and resources you have to focus on the new stuff to grow your business. The third row is about the cloud. Go is like purpose-built for the cloud. The libraries and integrations and architectures that Go enables, they were meant for the cloud. They weren't retrofitted for it later. So this means that you can realize the cloud's benefits faster and easier than you can in other languages. And finally, Go users are happy. They're happy everywhere, and they're really happy on Google Cloud. And everyone likes happy developers and operators. So with that, I'll hand it off to Michael for a deeper discussion on the Go compiler and PGO.
Thanks, Cameron. As Cameron mentioned earlier, my name is Michael. I'm a software engineer on the Go team at Google. And I'm going to dive into profile-guided optimization, which was added to Go in Go 121 last year. So profile-guided optimization, or PGO, is a category of compiler optimization techniques supported by a variety of different languages. With PGO, the compiler is using information about the runtime behavior of an application in order to improve the optimization decisions made during compilation. You may have also heard the term feedback-directed optimization, or FDO. FDO and PGO are just interchangeable terms for the exact same concepts. But before we get to profile-guided optimization, let's step back a little and talk about what we mean with just compiler optimizations in general. And in fact, before that, what exactly we mean by a compiler. So in the most general sense, a compiler is a program that translates source code from one language into some other target language. In Go, we're probably talking about the Go compiler, which you use with Go build. And the Go compiler translates Go source code into machine code for whichever target CPU, so an AMD 64 or ARM 64 CPU. On this slide, we can see a very simple example of an extremely basic Go function and the AMD 64 assembly that it generates on the right. And if you're not familiar with reading assembly, don't worry, I'm going to keep it pretty light. So we have this simple addition function. On the right, we can see the assembly. We have an add queue instruction, which adds the value of two registers together, and a ret instruction, which returns to the caller. This is pretty much as simple as a compiled function can get. Let's see a little bit more by putting it in context. So now we've added a call to the add function from main. And in the assembly output on the right, we can see in the main function is moving the arguments into some registers, calling the add function, and then finally getting the result and moving it to the memory location for the C variable. And the output we saw there kind of showcases a sort of central design decision of most mainstream compilers, including Go, which is that functions are the sort of core unit of compilation. So just as we use functions to organize our own code within a package, a compiler is also using the same functions to segment its compilation. So a compiler is going to compile each function independently into its own little block of assembly, and then calls between functions are handled with call instructions on the CPU that jump in between the different functions. And the compiler will also define some sort of calling convention, which is sort of a contract for how arguments and return values are passed back and forth to ensure there's a compatibility. But it's important to sort of step back and think, like, why does a compiler do it this way? Why not just say start with your main program and include every reachable function into one big giant assembly blob? Like, maybe the compiler could do better with that. There's a few reasons that compilers tend not to do this. First of all, it may be infeasible in many cases. If you consider a function that maybe takes an io.writer interface value, we don't know, the compiler may not know at compile time if that's going to be an os.file or a bytes.buffer or some other type. So there has to be some sort of dynamic jump to the right code at runtime. Second, even if it is feasible, one giant program can really bloat your binary size. If you think about some common function you have that's maybe called 1,000 different times in your program, if we include the contents of that function every single place it's called, we're going to make the binary a lot bigger than it needs to be, duplicating this code 1,000 times. And finally, and sort of most important for this talk, is that a lot of compiler optimizations are quite computationally complex, maybe even NP-complete. So compilers will often utilize heuristics to maintain fast compilation times by sort of doing an approximation to get a good result, but not necessarily the perfect result. And as the code size increases that the compiler needs to deal with for this optimization, those heuristics can start to fall apart and maybe generate suboptimal code. So encapsulating the code into individual functions that are compiled separately sort of helps manage this risk and keep the code size that the compiler needs to deal with simple. And because of that, most compiler optimizations apply only within a single function. So let's take a look at our first compiler optimization, which is inlining. Inlining is pretty much the exception to that separate compilation rule I just mentioned, where in certain very specific cases, a compiler will decide that it may be worthwhile to directly include the body of a callee into a caller function. So here we can look at an example of inlining the call to add. So on the right, we can see sort of an approximation of what the compiler is doing when it inlines the call. So it's taken the arguments to add and it's placing them in local variables, A and B, and then the body of add moves into the assignment, so we just have C equals A plus B. And now that we've done this inline, you can probably notice a potential opportunity here, which is that it's quite obvious now, just from the source code of main, that the value of C is just 3. We really don't need to do any computation, and we'd like the compiler to figure this out as well. As I said, most optimizations operate within a single function. So this wouldn't have been possible before, but now we can unlock optimizations that weren't possible before. So let's see what the compiler can do. This next optimization is called constant propagation. Constant propagation is a compiler optimization that replaces values that are known to be constants with the constants themselves. So here, we can see A and B have constant values, so the compiler will replace the uses of A and B with the constants themselves, simplifying the program. Now, the compiler at this point could emit an add instruction to add 1 and 2, but we know the result of this addition is going to be the exact same every single time. So instead, the compiler can itself evaluate that expression and replace it with the result. This is called constant folding. And so here we can see the final assembly code output before and after these optimizations, which is quite an improvement. When we started, we had some setup for a call, we performed an addition, we moved the result to a destination, and afterwards, we simply move the result to the destination. There's no call and really no computation left at all. Now, of course, this is a rather contrived example. A real-world code is probably not quite this straightforward. It's not going to have quite such an extreme simplification. But inlining still has opportunities to reduce computation, can often do things like remove if conditions whose conditions have become always false, and sort of simplify your functions. And a single inline site is probably not going to make much difference to your application performance, but the compiler will often do this in hundreds of different places, and the little small improvements can really start to add up over time. Okay, let's talk about another optimization related to heap allocations. So if you're not familiar, there's 2 places that memory for objects can be allocated in Go, either on the heap or on the stack. The heap is a fully general-purpose memory allocation location. Any object can be allocated on the heap, and the garbage collector is responsible for determining when that object is no longer used and will free its memory. On the other hand, the stack is a single chunk of memory allocated for a Go routine, with each Go routine having its own stack. Stack memory is managed during function call and return, so each function will use a fixed amount of stack space, and whenever that function is called, the stack size will increase to accommodate the space required, and when it returns, the stack size decreases, effectively freeing all the objects on the stack. We can see a quick example of how this works. On the right, the stack starts off as empty. When foo is called, we need space to store the A variable, so the stack size is increased, and we use 1 slot to store the value of A. When we call bar, we further increase the stack size to store the values B and C. And then when bar returns, we don't need B and C anymore, so the stack size decreases, and we've freed up that space. And finally, when we call bar again, we once again need space for B and C, and we grow the stack again. And now notice that we've reused the same part of the stack as the previous call, which gives us a really fast reuse of memory that didn't involve the garbage collector. But note that because of this, the stack has limitations. Because the memory is freed on function return, we must never place something on the stack if it can be referenced after the function returns. It can only be used for values local to the function. And we'll see an example of this in a minute. But if the stack has these limitations, why use it at all? Why not just put everything on the heap? And the reason is that while we try to make heap memory management as fast as possible in Go, stack memory management is basically the fastest possible memory allocator you can come up with. Because allocating on the stack is little more than addition and subtraction on function entry and exit. Meanwhile, heap allocation involves complex data structures to find free memory during allocation, and then a full garbage collector to notice the object is no longer referenced and free the memory. So it's always preferable to place objects on the stack if possible. So let's look at an example to show how the compiler decides what to allocate on the stack. This process is called escape analysis, because the compiler is trying to determine whether pointers to an object remain within a function or if they escape beyond the function return. So in this first function, we create a new foo object and then return a pointer to the object. This is clearly escaping the function. If the the object were to be placed on the stack, it would be freed as soon as new foo returns, and callers would get an invalid pointer. So instead, we have to place the object on the heap, and the garbage collector will be determined when it's safe to free the object. In the second function, on the other hand, we create a foo object and get a pointer to it just as before. However, the uses of the pointer, f, are all contained within the function. By the time the function returns, f is no longer used. So it's safe to put this object on the stack. This is great. It's going to be more performant than allocating on the heap. But that said, if you're a Go developer, you've probably seen hundreds of these functions that look like new foo, and you probably wouldn't write compute this way. Instead, you'd use the new foo constructor function to make a foo object for us. But this is really unfortunate for performance because the allocation is now moved back into the new foo function. And as we determined before, it can't safely allocate it on the stack. So we have to move it to the heap, and that's going to slow down our code. But this is where inlining can come in to help us out. If the compiler inlines the call to new foo into compute, it can once again allocate the object on the stack and eliminate the heap allocation. And it turns out that because stack allocation is so much faster than heap allocation, eliminating heap allocations is really one of the most impactful effects that inlining can have on an application. Okay, so we've seen a couple different compiler optimizations, how they can improve our code. And I mentioned earlier that a lot of optimizations use heuristics to decide what to do, and function inlining is one of them. If you recall earlier, one of the downsides to including a bunch of code in a function is related to code size. We might make the binary too big or slow down the compiler. So the primary heuristic in the Go compiler for inlining is related to code size. We consider small functions safe to inline and large functions not safe to inline because they might bloat code too much. But this is really quite conservative and probably results in missing some optimization opportunities. The more powerful heuristic to note here is that we really only care about the performance of hot functions, or functions that execute very often. If you think about it this way, if a compiler optimizes a function and makes it twice as fast, but that function is never called, then the optimization made no difference whatsoever. And it turns out in the vast majority of programs, only a small percentage of functions use the vast majority of all the CPU time. So if we take the Go compiler as a sort of sample complex Go application, in the Go compiler, only about 15% of the functions in the binary use over 99% of all the CPU time. And only 4% of the functions use over 90% of the CPU time. And this pattern is common across most programs. You often have code use maybe only one string initialization, or in configurations that you don't actually use in production, or the code is reachable, but only in really rare conditions that just don't happen that often. So if we can limit our inlining optimizations to only target the hottest code, we'll be targeting the code that has the highest potential impact and will limit the risk from bloating code size. Unfortunately, typically a compiler only gets source code as input. How is it going to know which functions are hot? And this is what sort of brings us back full circle. We want to know which functions are hot, which is exactly what a CPU profile would tell us about an application. If we can provide that profile to the compiler, it can use that information to guide its optimization decisions, and we'll have profile-guided optimization. Inlining happens to be one of the primary decisions that PGO informs in Go today. The Go compiler will use the profile to determine which functions are hottest, and it will focus its inlining efforts on those. So let's see how this works with an example application. I'm going to use just a simple HTTP server for this example. Since we're talking about PGO, I made a server that analyzes a Go profile and reports the hottest functions in that profile. I've skipped most of the code here on the slide for space, but there's a couple things to note. First of all, this is just a standard net HTTP server. I'm sure you all have written something similar many times. In the request handler, we read the request body, parse it as a pprof profile, do some processing to group by function, and then respond with the 5 hottest functions. Second, notice this pprof package we're using. If you're familiar with profiling in Go, you've probably used the Go tool pprof to explore data in a profile. This package is provided by the same tool for parsing those profiles. It can be super helpful if you're looking to do analysis that the tooling doesn't support. And finally, notice this net HTTP pprof import. which is the easiest way to add profiling to a web server. Simply importing this package will add some debugging HTTP endpoints for collecting profiles to your server, which we'll use in a bit. So here's a quick peek at what the server does. If I upload a profile to this server, I get back a response that shows the top functions. In this case, happen to be in the Go runtime, pprof package, and in compression. So now let's collect our own profiles and use PGO. So the goal of PGO is to provide the compiler more information about how your application behaves in its production environment. So we strongly recommend that you collect profiles from your real production environment, if at all possible. Now, of course, my toy server doesn't have a real production environment, so I just wrote a small load testing tool to put it under load, and then I'm going to collect the profile. While the server is loaded, I can fetch a profile from this URL endpoint, which was added by that the net HTTP pprof import I showed earlier, which is going to collect a 30-second profile. And now, while it isn't required to use PGO, let's take a quick look at our profile just to get a sense of where the program is spending time and maybe how we might optimize it manually. As I mentioned before, Go ships with this pprof tool for analyzing profiles. We'll look at a couple views in here. One of the most generally useful visualizations in this UI is the flame graph view, which you may have seen before. This visualization was originally created by Brendan Gregg and is used in profiling tools across many different languages. If you're not familiar with a flame graph, a quick overview. Each box you see is a stack frame with callers above callees. For instance, in the upper left, we see a serve method calling 3 different serve HTTP methods, and finally the upload post function, which is the one I showed a few minutes ago. And the width of the boxes on the screen give the proportion of total CPU time spent in that function and in any of its callees. So the wider the box, the more time spent there. So we can take a few high-level takeaways from this. First of all, we can see about 80% of the time is spent in our HTTP handler. The functions on the right, I happen to know, are mostly the Go garbage collector. So one thing I may do if I wanted to dive deep into manually improving performance is investigate why we're spending this time in the garbage collector. And within our handler, we can see about half the time spent parsing the input with gzip decompression, protobuf unmarshalling. Probably not something we can really avoid, but maybe it can be made faster. And most of the remaining time is spent on processing that I personally added just to determine the hottest functions in the profile. This would be a great place to investigate if I really need to do all this work or if I'm doing some unnecessary work and could make that faster. So this is a sort of a high-level starting point for manually optimizing this program, but that's not why we're here. Let's see what the compiler can do with this profile. So to use PGO, recall that we used a quick curl command to collect a profile. Once we collect that profile, all we need to do is name the profile default.pgo and place it in our package main directory. Go build will automatically use a default.pgo file as its PGO profile for the build. Now, we recommend keeping your profiles alongside your source code in the repository in order to ensure that anyone who checks out your code can reproduce the exact same build. But if that isn't possible for some reason, there is also a go build-pgo flag that can directly get past your profile. So once I built with PGO, I measured a couple different CPU and latency metrics on both the original server and the PGO optimized server, which I'm comparing here. And we can see about a 10% improvement across the board. Now that's pretty good considering I just ran 2 or 3 commands from that previous slide. And PGO is optimizing some low-level details such as inlining. So the high-level observations I made on the flame graph probably still apply, and I could probably improve this further if I was manually optimizing. And I will note that results do vary with PGO. The best applications we've seen get up to about 15% improvement. On the other hand, some applications we've seen get about 2% improvement. It's sort of difficult to predict the impact that PGO will have due to the kind of low-level nature of the optimizations, but luckily, it's pretty easy to just try it out yourself and see what kind of impact you can get. And as the Go compiler continues to improve, we expect the compiler to continue making more use of profile data for different types of optimizations to keep unlocking more improvements. And now if we take another look at a profile of our PGO optimized server, we can sort of look under the hood to get a sense of what has changed within our application. So here I'm using the pprof tool again. This time I'm performing a diff profile to compare a profile from before I optimized the server and after I optimized the server. In the middle here, we can see the total CPU time has dropped by about the same 10% we measured before, which is good. And on the left, we can see the magnitude of the change in individual functions within the program. So we can see we've got improvements within the Go runtime, the pprof package dependency, and so on. And one exciting aspect of PGO is that because the profile covers your entire application, not just the code you wrote, but all of your dependencies and the Go standard library, so do the PGO optimizations. So you'll often get improvements in code that you've never even seen before. You may also notice that the fourth function on this list here, the runtime internal atomic one, actually got slower instead of getting faster. These sorts of regressions are sort of to be expected. Ultimately, inlining is a compiler heuristic, and it can't really be certain it's going to make an improvement. But the critical aspect here is that in aggregate, the improvements outweigh the regressions, which is very much the case here. And with that, I'll hand it off to James, who's going to talk about PGO with Google Cloud.
Thanks. So we saw a bit of Go, and we saw how PGO can help improve the CPU utilization of your applications. And so what we're going to do next is see how you can deploy some of those efficiencies to your production Go applications. And so for this talk, we're going to talk about how to use it with Cloud Run. Cloud Run is a great option for deploying your Go application because it's simple, automated, and hyper-elastic. It's simple because if you want to build a container and deploy it, great. If you don't, we also have a tool available for you to automatically look at your code, compile it, and deploy it with Google's opinions on how to compile a Go app. It's automated. Run any container. Don't worry about the infrastructure. Set it and forget it, really. And the key thing is you pay for what you use. If you serve traffic, you get billed by the CPU second. If you don't, it scales to 0, and it'll be ready for you when you need to have it running. And lastly, I want to mention that's hyper-elastic, on-demand availability. You don't have to pre-allocate. It's really there for any on-demand needs that you have. So we're going to take the same example that we just saw and deploy it to Cloud Run. As you can see, it's as simple as one step. I don't want to build containers all day, so I'm using the source deployment option that we have here. It's as simple as doing gcloud run deploy --source in your local folder. And you'll see that we're using BuildPacks, which is an open source standard for containerizing applications. And what it's doing here is going to be pulling down the latest version of Go. So you don't even need to necessarily care about which version of Go you want to use. This will always give you the latest. And we're done. And we're going to be serving traffic right away. And so what we're going to do is take advantage of the seamless integration that we have with the Cloud Profiler and access the same flame graph. And so instead of optimizing against synthetic traffic, what we can do is actually have collected data from your actual traffic on your actual Go application and download that same profile. We're going to rename it to default.pgo and just do a quick redeployment. Now, because I'm using the source option, it's going to be able to detect the same default.pgo and compile it with the profile as a part of the Go build process. Oops. And so when we redeploy it and run it through the same traffic test, we see a 10% decrease in the billable container time. So those savings went from on your desktop tests only to in production, saving you a bit of CPU utilization, billable hours. And so that's all. I'm going to hand it off to Cameron to close it off.
All right, awesome. Thank you, James. And a quick recap before we close. So now you know how the Go developer platform enables end-to-end solutions out of the box, right? The tools, the libraries, the integrations, all of that. You know why you would want to use Go, especially for your cloud-based workloads and especially for your critical systems in your stack. Michael showed you how the Go compiler optimizes your code. And he showed you how you can use a profile of a running Go application to optimize even further using PGO. And then James shows you how you can use PGO on Google Cloud to reduce your billable time using services like Cloud Profiler and Cloud Run to save yourself some money. And that's all we have. Thank you very much for coming.